Hey, it's welcome, welcome. Yeah, so this is a very exciting video because in this video we're going to learn about a very powerful but fun tool called the method of Lagrange multipliers. Now, recall what we did in the optimizations topic in single variable calculus. What we did in optimization is we maximized and minimized single variable functions given a constraint. That's exactly what the method of Lagrange multipliers does, but only for multivariable functions. And therefore, the method of Lagrange multipliers is simply optimization for multivariable functions. It's a way to maximize and minimize multivariable functions. Yeah? Alright, cool. Now, this video is dedicated to how the method works. It doesn't explain why the method works. If there's enough interest, I'll dedicate another video to explaining why the method works. But there are two approaches on how to use the method of Lagrange multipliers, so there's enough to discuss on how the method works here in this video. Yeah? Okay, cool. As I said, two approaches for maximizing or minimizing multivariable function given a constraint. And as I already said, just like single variable calculus, this is just optimization for multivariable functions. Yeah? Okay, and recall what we did in single variable calculus optimization when we looked at an open top box. Because this is the example that will be given here in this video. We're going to look at an open top box, but also a closed top box, and we're going to use the method of Lagrange multipliers to minimize surface area in both cases. And I'm going to offer, as I said, both examples in this video. But I just want to point back at what we did in single variable calculus, because we did do this problem of minimizing surface area in single variable calculus given a fixed volume. But we made a very important assumption when we minimized surface area of a box in single variable calculus, which is we required that the box have a square base. And that's because, well, remember, the volume would be the constraint function, and it'd be like x times y times z equals some constant. So you have a function of three variables, x, y, z equals some constant, and then surface area. If the box does not have a square base, surface area would also be a function of three variables. But then that means you have two equations and three unknowns, and there's no way to reconcile that. That's why in single variable calculus, we had to assume that our box had a square base, because then that meant that we only had two variables, and we could use the volume constraint to get rid of one of the variables, and therefore make the function surface area, which we're trying to minimize or maximize, into a function of a single variable. But here, lucky for us, because we have the method of Lagrange multipliers, we don't require that any of the faces of our rectangular prism be squares, because, well, we can work with multivariable functions. Yeah? And how the method works is basically executing, sorry, I was trying to talk too fast, executing exactly what I'm about to show you in either of the two approaches. Okay, so the first approach is this. What we're trying to do in both approaches is the same, which is maximize or minimize a multivariable function subject to a constraint, right? And in the first approach, what you should do is solve the four equations that I'm about to show you and the four unknowns. In fact, it turns out that both approaches lead to the same conclusion, and in fact, towards the end, they're the same. They're just like slightly different setups, slightly different ways of setting up the same thing, basically. And you'll see exactly what I mean after I reveal both approaches. But here are the four equations and the four unknowns that you have to solve. There are three equations in here, and then a fourth one is the constraint function itself. Lambda here in this first equation is called the Lagrange multiplier. And yes, you heard me right. I did say four equations because there are three equations in here. Remember, this here, which is red, is del f, means the gradient, right? And that's just a three-dimensional vector. Since f here is three-dimensional, that gives you the partial with respect to x, the partial with respect to y, and the partial with respect to z. That's all that del f means. It's sort of like the slope for a multivariable function. Yeah? Okay, alright. Now, well, if del f means this, then del g means this, right? And therefore, del f equals lambda times del g will mean that this here is equal to lambda times this here. Notice that this is a vector and this is a vector. So if I multiply the second vector with lambda, it's kind of like light. So like, let me display it all the way. That is, like if I multiply this here by the constant lambda, then I could put the lambda into each component here. And so then this here, this equation, which is this here, would mean that the partial with respect to x of f is equal to lambda times the partial with respect to x of g, right? So there are three equations in this, and I'm going to show you all three of them, so no panic. So the first equation from this is this. The second equation is this, right? About the partial with respect to y being equal to lambda times the partial with respect to y here, right? For one function being equal to lambda times the other function's partial for that same variable. You get it. And then the partial with respect to z of f is equal to lambda times the partial with respect to z of g. Right here, that's the three equations from here, 1, 2, 3. And then the constraint function itself, that's the fourth equation. And yes, there are four unknowns. The four unknowns are x, y, z, and lambda, right? Okay, and we've got four equations and four unknowns, so we know we're safe, we're good, we can solve the equations, yeah? So that's the first approach, and so that's all you got to do, and so I have summarized the first approach here. That is, we want to maximize or minimize f here subject to this constraint on g, right? And so this would be like the surface area function, and this would be the volume because it's a fixed volume, and therefore you have the constraint on the volume. And what you have to do is solve the four equations that are in this box here. And I already said with sufficient reasoning why there are four equations here. So that's it for the first approach. Now the second approach. Okay, a very, very brief story. Now, in college, I tried to triple major in math, economics, and statistics. And of course, I finished the math major, and it was theoretical math because it was really fun. And even if I wanted to go out with my friends and so on, I still made time for my problem sets and worked really, really hard and enjoyed every minute of it. But I wasn't enjoying economics and statistics as much, so I was only 2 courses shy of finishing both the statistics and the economics major. So I was only 4 courses shy of a triple major, and like I did that because I got bored with the economics and statistics majors, and in particular the economics major, which is why I am telling you this little story, was basically in every course about Lagrange multipliers. And yes, understandably, like what economics is about is like maximizing, minimizing multi-valued functions given a constraint, so no surprise that like Lagrange multipliers show up a bunch of times. But literally every course I took was about Lagrange multipliers using this second approach. And so for all practical purposes, I recommend that you use this second approach. And it is exactly the same as this first approach. It's just the way you set it up to start makes it look different. In fact, once we get to the example, I point out how the two approaches are identical. But the second approach is this, and this is what I did like pretty much in every econ course in college, which is, well, again, the goal is to minimize or maximize this function subject to this constraint. Now, what's very, very important that I point out in this second approach is, well, I'm going too fast, but yeah, in this second approach, the function g is the constraint function minus c. So here, g of x, y, z, notice, is equal to 0, whereas here it says g of x, y, z is equal to c. So in this g, right, in the second approach, this g function is this g function minus the c. That way it's equal to 0. Very, very, very important, because if you set it up in any way different from the detail that I just pointed out, the two methods or the two approaches are not going to be the same. But yeah, your goal is the same as before. You're trying to maximize and minimize this function to this constraint, right? Given this constraint, again, I said the note about the constraint needing to equal 0, right? You need to rewrite it so that it equals 0, but otherwise what you do is you create what's called the augmented function, the L function. And the L function is going to be a function of 4 variables, x, y, z, and lambda. And the L function is going to be made of your f function and your g function in this manner. And then all you have to do once you figure out what your L function is, and notice your L function is very straightforward, surface area function minus lambda times the volume function, where like the constant on the volume, the constraint is also on the same side as xyz. So if like the volume is xyz is equal to 125, then this g here is going to be xyz minus 125. That's just multiplying lambda. But otherwise, writing down this L function is very straightforward, making it that is. It's just f minus lambda times g, where g has a detail I pointed out here in the second approach. And then what you do after that is take the four partial derivatives of L, and four partial derivatives with respect to the four unknowns. That's the partial with respect to x, the partial with respect to y, and then partial with respect to z, and the partial with respect to lambda. I feel like with Eddie Murphy and Bowfinger, where he was like having to say like the phrase "keep it together, keep it together, keep it together" really fast. Like yeah. Okay. Anyway, I'm saying like I'm having to say partial. Okay. Enough. All right. So find the four partials, and I can't talk anymore, and set them all equal to 0. So you'll see what this looks like in practice. But this is it for the second approach, because well, once you do this, then you'll be able to find the solutions xyz, just as you'd have these four equations that get you to xyz, right? They'd also get you lambda, but that's just en route to getting xyz. What you really care about is getting xyz, right? So like you get xyz and lambda either by this setup, the first approach, or by this setup where you write the L function and take the four partials and then set each partial equal to 0. Again, I'm going to walk you through a practice problem in this video, so you're going to see how exactly this works. But of course, either approach is going to get you the solutions xyz, first approach or second approach, and you can check whether or not the xyz solutions that you found are in fact a maximum or a minimum using what's called, or what I'm calling, the multivariable second derivative test. I'll dedicate a different video to the multivariable second derivative test, but it's pretty straightforward. It's like an equation made of second partials, and you just have to plug in xyz and that equation, and it will tell you whether or not you have a max or min or a saddle point. Yeah, okay, cool, or a saddle. Yeah. Anyway, again, a different video dedicated to the multivariable second derivative test. But as I said, both approaches are the same, and in fact, they lead to the same four equations. We're going to see that they in fact lead to the same four equations in the example that is about to come. But yeah, like as I said, I'd use the second approach because it's just like easy to write down the L function and get started. But the first approach is just as good, and they both get to the same place, most importantly, right? And just as we like succinctly summarize the first approach, let's succinctly summarize the second approach, so we have them both to look at as we do our example. As I said, our example is to minimize surface area on a rectangular prism that's a box, and let's start assuming that the box has a top cover. So that's pretty straightforward. If you have xyz as the three edges, then you know this is how you'd label the faces, right? XY and XY, front and back, and blah blah blah. And so that's easy enough. And so then that means that the surface area, and as I said, we're going to use the second approach. The surface area is going to be this function, and that's what we want to minimize. We want to minimize surface area, and our constraint is that the volume of the box is 125 whatever units cubed, and so that means our g function is xyz minus 125. As I said, in the second approach, you need to have your g function written so that the constant is on the same side as the variables, right? And therefore on the other side is 0. Okay. I explained that sufficiently. So in the first approach, c here would be 125. That's what I'm saying. And in the second approach, there is no c. It's equal to 0, the g function, right? The constraint function. Yeah? Okay, cool. But then constructing the L function is pretty straightforward. I was just pointing out here that, like, well, just so that it's easy to follow these boxed and circled methods. In fact, this boxed method, I'm calling the surface area function the function f, That way, you know, it's just easier on the eye, no other reason. And maybe it's more work to write SA than F. Okay, but whatever. These are details, not important. But yeah, we get the L function to look like this, right? And sorry for forgetting to highlight that lambda right there. But yeah, otherwise, you know, it's pretty straightforward to see why this is the L function. The L function is F minus lambda times G. And so that's F here, the surface area function, minus lambda times the G function in this manner, since we're using the second approach. And so lambda times this is going to be this, and then it's a plus here because, well, remember this is a minus lambda, so when we distribute it to this part, it's going to turn this minus into a plus, right? Now obviously the 125 will be multiplied by lambda here, where the lambda here should be highlighted, but not a biggie, right? Okay, and then what we said from here is that you find four partials. The partial with respect to x, and let me talk you through that a bit more carefully. And what we said is we set the partials all equal to 0. That's why you have equal to 0 here. But yeah, the partial with respect to x of this means we'll treat all other variables as constants, other variables that are not x. So in this part, 2y is a constant, so you have 2yx really, and so the derivative of that is going to be 2y, and that's what I've got. And then in this part, 2z for very similar reasoning, and then this part minus lambda yz, right? And this is just a constant, as is this, because neither this nor this contain x's, and so these are both 0 when we take the partial with respect to x. And so this is what we get, and as I said, we set the partials equal to 0, and that's why you have equal to 0 here. Okay, so very similar justification would show why the partial with respect to y of L would look like this, and then the partial with respect to z, and then the partial with respect to lambda. Now notice that the partial with respect to lambda would mean that this is 0, this is 0, this is 0, and in this part we get minus xyz, and in this part we just get 125 plus 125. So it's minus xyz plus 125, and when we set it equal to 0, what we get is xyz is equal to 125. But that's just a constraint function. So the partial with respect to lambda, setting that equal to 0, what that gets us is the constraint function. In this manner, you can see that the two approaches are identical because, well, at least the constraint function here that we get back by getting the partial with respect to lambda to equal 0, that's exactly as just writing down the fourth equation here. And the others are equivalent to the three equations you get from here. Yeah? Okay. Yeah? Okay. But let's finish solving. And so notice that from this first partial with respect to x equaling 0, we'd get this equation, right? And all I've done is I've taken this and I've added this to the other side, right? And then what we could do here is we could divide both sides by yz, and when we do, what we're going to get is this version, right? Like, I'm going a little too fast now. Yeah, if we take this and divide both sides by yz so as to isolate lambda, we would get this. That is 2y over yz is going to be 2 over z, plus 2z over yz is going to be 2 over y, and obviously lambda yz over yz is going to just be lambda. Jesus Christ, I cannot talk like today. Like, okay, well, I can. So let's keep going. So second and third equations similarly done, and by that I mean this one and this one, right? Like similarly dealt with in this manner, and then like turned into this would look like this one, right? And then they would look like this one. So I basically move this guy to the other side and divide both sides by xz on the resulting equation, and did a similar thing on this to get these two, like in case I'm going through that a little too fast. Now, obviously, lambda here is the same as this lambda, so what we could do is we can set this first equation to this equation, and we could also set this equation to this equation, and that way we can solve for x, y, and z. And so doing exactly what I just said, first setting this here is equal to this, because, well, this here is lambda and so is this, we get this equation. And notice here we can subtract 2 over z from both sides, and what we're going to get is 2 over y is equal to 2 over x. And so then the resulting simpler equation will look like this, and obviously cross multiplying here or whatever else you do, it's obvious that y will have to equal x. And then, as I said, setting this equation to equal this equation, what we're going to get is this situation. You'd get an equation like this first. Specifically, you'd get 2 over z plus 2 over x is equal to 2 over x plus 2 over y, and then you can subtract 2 over x from both sides to get this equation. And from this, it's easy to see that z has to equal y, right? Okay, so z equals y. Great. So y equals x and z equals y, so that means x equals y equals z. So yeah, that means that if we now plug into the one unused equation, which is the constraint equation, which is this, since x equals y and y equals z, that means that x, y, and z are all x's. We have x times x is equal to 125, and so we get this, which means that x is equal to 5. Now, I'm going to show you slight different varieties of this same problem of like minimizing surface area, but we can already make a general statement here, which is that so long as you have a surface area defined in this manner, that is like the box does not have any side missing, and each of these parts are multiplied by the same constant, that what you're going to get is that the minimal surface area is given if all the edges have the same size. So for example, if the box has volume 300, then the minimal surface area is given by all three edges being equal, and specifically equal to the cube root of 300. Yeah? Okay, cool. So that's a general result that you can take home with you and trust me on. But here it's clear that the solution is 555, and as I said, you can use the second derivative test for multivariable functions, which I will teach you about in a different video, to check whether or not 555 is in fact a minimum. Yeah? Now, before we conclude, let's consider what would happen if the box had an open top, right? And all that would do is, in our surface area equation, it would change one of these 2's into a 1, right? That's all that would change. And so, like, this is the situation we'd have. And so, like, the bottom face is YZ, and so it would be missing 1 YZ here. So instead of 2 YZ here, we should have just a YZ in this part. In fact, instead of doing that, what I've done is I've changed the weight on the XY. So instead of a 2 here, I changed it into a 1. It's a similar impact as instead of having 2 YZ, having a single YZ. What we're doing is instead of having 2 XY, we're having a single XY. Same impact, right? And so our surface area would change in this way. Our surface area equation, our f function, would change in this way. That's all that would change, because we're still working with the same volume constraint. And so obviously, if you work this out, you would work it out in the very same manner that I just showed you, right? Like you'd set up your L function, blah blah blah, and the answer is going to be different. It's not going to be making all the edges the same, right? That much you could understand, but the approach and everything else is the same. So I'd be repeating myself a lot if I walked you through how you would do the slightly different variety. So instead of walking you through the slightly different variety, what I'm going to do is I'm going to show you a third variety, interesting choice here, because well, what we're doing this time is like we're building prices into the sides of the boxes, or the faces of the boxes, let's say. So we still have an open top box, but now the sides all cost $4 and the bottom face costs $8. Well, so what that would mean is we take this here, not this one, but this one here, and we multiply the one that doesn't have a 2 with an 8, right? And then the rest of them, this one and this one, we multiply by a 4. So when we do that, this is what we're going to get. Our surface area function is going to look like this. Noticing that that means that we have an 8 here, we have an 8 here, and we have an 8 here. So the weights are going to be the same. Remember when we're doing our algebra earlier, and the one we worked out all the way, we had like a 2 over x equals 2 over y. Instead of that, what you're going to have is an 8 over x is equal to an 8 over y, blah, blah, blah. And so what I'm saying is, because this number here is the same as this number here, which is the same as this number here, we're still going to get the same answer as 555. Yeah? Okay, cool. All right. Of course, you know, if these numbers aren't all the same, As I said, these I call the weights. So if the weights on xy, xz, and yz are not the same in this surface area equation, or surface area function, I should say, then like the answer would be different from 555. But otherwise, if the weights are the same, the answer is still going to be 555, because, well, it's as if like we're scaling that first surface area equation we wrote down with 2, 2, 2. Yeah? Okay, cool. I hope you enjoyed this. Lots more multivariable calculus to come, and maybe another example on Lagrange multipliers. All right. Have a great day. Take care.